reduced mass. So when we have got two masses, M1 and let's say M2, and we want to actually consider an equivalent mass of these two, the formula that we have seen is this. This is not something new, which you might have already seen it before. And then this mu is actually a representation of the reduced mass. And for two mass system, it is M1, M2 divided by M1 plus M2. Okay. And this is called the reduced mass of two particles. Using a similar concept, you can also find out the reduced mass of three particle, four particle system, and so on. Okay? But then we are not doing it right now. Right now it's just out of scope. Okay. So based on this, yes, the last class, this is something which we have already done. We actually found out what is the equation of motion, and we saw that this is something which is similar, right? So this is your mass, this is your acceleration, and that's your force, and that's the distance. And if there is a minus sign, we are talking about a attractive force. So whenever we have got two masses, let's say M1 and M2, okay, and then they are actually under the effect of, let's say, the universal law of Newton's law, universal Newton's law of gravitation, they're definitely talking about an attractive force here. Okay, so we are considering this, and this will actually represent a one body problem. So we are considering two masses, but then if we consider one frame of reference, we can consider a single equation of motion. So similar to the equation of a single particle mu, and we have at a distance r. For a single particle it's m, but then here we have got mu, and they are separated by a distance r, two masses. Okay? And we do have one inertial frame of reference. So it's important that we are considering an inertial frame of reference. That means the velocity is more or less constant. Okay, that's very important. Now let's take an example. Let's take a practical example, and let's consider M1 and M2. And let's say M1, which is nothing but the mass of electron. So you know the electron mass is 10 to the power minus 31 kg order-wise, right? And M2 is nothing but proton, okay, of the hydrogen atom. So what is the mass of proton? 10 to the power minus 27 kg. So if it is minus 31 and minus 27 kg, that means electron is actually having a very less mass compared to proton. Okay? It is also one of the reasons that we actually, when we study about an atom, the mass that we consider is actually that of proton and neutron. And many a times we do ignore the mass of electron because it's very less. Okay. So even if you have a mass, let's say in comparison, if this is one mass of proton, the other one is 10 to the power 4 orders less. So this will be 0.0001, right? Something like this. So if you add them up, this will be almost equivalent to 1. So that's why the reason that we actually ignore it. Okay. So if we consider this idea, we can again consider this reduced mass formula. Mu is equal to m1 m2 divided by m1 plus m2. And I can actually just take this m2 at the denominator, right? So I can divide this part by let's say m2. Okay. So I've taken m1 m2, so I can divide this by m2 and I can divide this by m2. So it will be nothing but 1 plus, okay, so 1 is from here, and this will be nothing but m1 by m2. Okay, this is m1 divided by m2. Okay, that's important. So you can just take it to be 1, okay, m1, and then this is equivalent to this. So what happens is, if you're doing an expansion, okay, this is, let's say, this for this, the expansion is this. I think this is something which you already know. The expansion is 1 plus x to the power minus 1. So if you take it at the numerator, this will be 1 plus x to the power minus 1. Okay. And then if you expand it, you get 1 minus x. Okay. And then minus factorial 2 and so on. But we are ignoring the higher order term. Okay. And then we are just considering the first two terms. So 1 minus m1 by m. So this is an expansion of this. Okay. So I think we remember this. So just expand this and put the value. Now you know this m1 by m2 will be actually small. Why? Because m1 was electron, right? And m2 was actually proton. So proton mass is much larger compared to electron. So you're dividing a small value by a very large value. So we can actually say that it's a very small quantity. So this one will be relevant here, but not m1 by m2. So if you do that, you see that the reduced mass of the system is nothing but just m1. So what does it tell me? It tells me that if I'm considering a two particle system, and if one of the mass is very large compared to the smaller mass, I can always ignore the smaller mass. Okay. Now why this is important? Because when you do calculations or numerical, okay, you do this, and even if you include m2, you will see that the answer will be very close even if you have considered only m1. So you have to understand that what kind of question is asked. So in your entrance exam and all, they do ask these kind of questions. Okay, they will give you two masses, one is large, one is small. You can straight away ignore the smaller mass and do your calculation. You'll see that the answers will match the option that you have. Okay, so this is also important from that point of view. So this is an example of reduced mass, which is again important. Okay, and what we are going to do now is something which we have already done. Okay, so probably this will be just a repetition, but then we are going to do something different here. So whatever we have done till now, in case of central force, we have just considered the form of the force. So we have just said that okay, the central force is nothing but Fr, right? So what we are going to do is we are going to consider what is the form, which is 1 divided by r square. We are giving it a definite form. So what force is that? It might be two masses under the action of gravity. The force acting between them would be nothing but capital G into m1 m2 divided by r square. So the force is inversely proportional to r square. So that example can be taken. Or you can consider two charges q1 and q2 and they are separated by r. That example can also be taken. And both of them will actually give you an example where the force is this. Okay. So this is what we are going to look into it now. And then this is nothing but a repetition, but still we'll just repeat it. And I will give you something additional there. We'll do a comparison between the Lagrangian and the Hamiltonian, and we'll see that both of them are more or less giving you the same equation of motion. Okay. So this is what is happening. Uh, just so what happens is let's consider a particle of mass m. Okay. So let's go step by step. So whenever you write down in your exam, it's important that you at least maintain some sentences. Okay. So we have got to consider the particle of mass m, and it is basically moving in a plane. Okay. So we are basically considering a two-dimensional motion, and it is attracted towards the origin of coordinate with f proportional to 1 by r square. As soon as I say 1 by r square, I'm talking about a central force problem. Okay. And then we have seen before that we actually consider the plane polar coordinate for this. So I think this is also very much okay because you already know that the kinetic energy for such a system under the spherical polar coordinate is nothing but half m r dot square plus r square theta dot square. Now, as I promised before that I will actually show you the form for potential if we have the force, and we already know about it. Okay, so if you want to find out the potential from the force, you can do it in this way. Okay, we can use this calculation and do it. Okay, now since this is an attractive system, we do consider a minus sign there. Okay, and then integration of infinity to r f dr. Okay, so what is the or in general we can say what is the work done in bringing a charge. Okay, if it is a charge, or if it's a mass, then what is the work done in bringing a mass from infinity, okay, to a point r. So this is how we define it, right? So fdr. So this is minus integration of infinity to r. Now the advantage is we already know what is the form of r. We'll just replace r, do our integration, and we see that this is the form of potential. This is the form of potential. Okay. So this is I think clear because if you remember from your memory that when you did your Coulomb potential or Coulomb force, the potential is nothing but kq divided by r, right? And when we take force, it is kq1 q2 divided by r square. So definitely the potential form will always be 1 by r. So whenever you are doing any kind of calculation, please make sure that the form doesn't change. Okay, that's very important. Negative one, so it is more or less attractive in nature. Okay, so that the calculation, I think I don't need to explain this. I've just done it so that it's more clear. And then we can actually write down what is my equation of Lagrangian. So mind you, whenever you are given a form of the force, it's important that you find out what is V and then you put it into the Lagrangian, okay, to avoid confusion, to do a clear calculation and so on. So it is L is equal to T minus V. So this is T V minus V. So minus, and then the potential has got a minus in front of it, minus K by R. So it will be plus K by R. So now we'll get back to our traditional calculation. We'll just we are going to find out the equation of motion using Lagrangian. Okay, we're going to find out the equation of motion using Lagrangian. So how do we do it? Simple. Del L ddt of, let's do it this way, ddt of del L del r dot minus del L del r, and ddt of del L del theta dot minus del L del theta. You don't need to understand much here. You can just simply do the del L del r dot here, del L del theta here, and then just replace it, right? So this is simple. theta is a cyclic coordinate, so del L del theta is 0. Okay. So I hope you remember these terms. Del L del theta is equal to 0. That means theta is a cyclic coordinate and all those stuff. Okay. And then just replace it. So this is something which you have already done. I don't need to explain this much. And then we can actually simply write down what is our equation of motion. So finally, this is already there in your copy. You can check. This is our equation of motion. Okay. So we have mr double dot minus mr theta dot square plus k by r square is equal to 0. Previously, we had just minus fr. Okay, minus fr was the equation of motion. That's important. So this is the equation of motion for a particle, and we have written this equation in terms. We have two equations. One is from that r coordinate, and one is from the theta coordinate. We have got two generalized coordinates. Okay, so this is the equation of motion of a particle under central force. The question arises that in your exam, if I ask you derive the equation of motion of a particle under central force, do I derive this or do you derive the last sum of the previous term? Of them, okay. But here you have to mention that the force is considered to be 1 by r square. Okay, but it's preferable that if I ask you a very general question that what is the equation of motion, then just simply use it as FR and keep it simple. You don't need to do those additions and calculations. But if I then specifically ask you the form of the force is given to be 1 by r square, then you have to show this definition. It should not be very difficult to understand this. And I would suggest that this particular equation, you try to solve it and find it out on your own. That's very important. So this is an equation which we found out using the Lagrangian. In the last chapter, we did the same, but we did it using the Hamiltonian. And if you remember it, we found out this form. This was the form of the equation that we found out. Now, is this form equivalent to this form? Okay, the first one, equivalent to this form. The answer is yes, because this is mr double dot is equal to m v theta square divided by r plus fr. So fr I can straight away write it down. Okay, I already know it. But then what is v theta? So v theta, I told you the last class that v theta will be nothing but the linear momentum. We can write it linear velocity. It can be written in terms of the angular velocity as r theta dot. Okay, that's important. So I think I don't need to explain this. This figure is self-explanatory. Okay, if the angle is very small, okay, the angle is theta. Okay, the angle is small, so sine theta can be considered as just theta. So you can simply write it down. Theta is equal to perpendicular divided by hypotenuse. Okay, or I think I should tell you opposite side divided by the hypotenuse. Okay, so opposite side is x here. If you're considering a very small displacement, it is almost a perpendicular line, and then it is nothing but the distance from the center. So x is equal to r. Okay. So when you differentiate this, you get dx by dt, which is v, is equal to r theta dot. Okay, so please remember this. R does not change, theta changes. So this is a from rotational motion. Okay, I cannot explain this much. Okay, so we can replace it here, and then we have got this equation, and then we have got this equation, and finally I know the form of fr is nothing but minus m. So if I replace it here, I get mr double dot minus mr theta dot square plus k by r square is equal to 0. Okay. And if I write it down in this form, does it imply this? Yes. So if I ask you question, let's say, show that the equation of motion of a particle under central force is the same when calculated by Lagrangian or by Hamiltonian. Okay, so that will be a descriptive question around. Okay, because you have to find out the Lagrangian and then you have to find out the Hamiltonian and show that both of them are equally the same. So you have to do these additional steps. Okay, so please don't forget your basics because this talks a lot about basics. So I preferred explaining this. I think this is important. Okay. So this I've gone a bit fast because we have already done it before, but now I'm going to go a bit slow and we are going to understand this. Okay. So what are the features of central force? So I told about being it conservation of energy, conservation of angular momentum, but I need to prove it, right? And proving is actually not very difficult. We are just going to prove it in few lines. Okay, because we are going to use this property in order to derive Kepler's law. So if you know Kepler's law, there are three laws and they are related to the laws of planetary motion. So if we are going to prove that law of planetary motion, we are going to use the concept of conservation of energy, conservation of angular momentum. That's why I'm going to prove it now. Okay, features of central force. So the question is, what are the features of central force? Okay, that might be a question. Or I can ask you, what are the features of the central force? Prove them. Okay. If I just ask you feature, probably this is just a 2-mark question. Okay? But then if you prove them, might be a 4-mark question, because even the proof is not that long. Okay. So let me just show you to this. But then before I show it to you, I think all of us remember this, that whenever I am representing a unit vector by r cap, and if I want to have a, let's say I have got a equation of, let's say, I cap plus j cap plus k cap. Okay, I want to represent it in terms of the unit vector. You can simply take the this value, this vector value, this vector divided by modulus of r. So modulus of r for this particular equation would be root over of 1 square plus 2 square plus 3 square, right? Sorry, root over 1 square plus 1 square plus 1. It will be root over 3. So whenever you write down a vector, unit vector, in terms of the vector itself, you can just simply write it down as r bar divided by r. Okay, modulus of r bar divided by modulus of, okay, or just r. So this is a representation which we already know. So if I want to represent a force in a particular direction, because force is a vector, I can always represent it as F bar is equal to F into R. So that's important. Okay. So let's go back to this topic, and we talked about conservation of energy. So what do I mean by conservation of energy? It means that the total energy will more or less remain constant. So if you remember, or you actually would be doing it also in your mathematical physics, you know, there is a operator which we basically write it as delta, right? The reverse delta, and we basically call it as the gradient, right? So whenever we have it this way, we can simply write it down as I delta x, okay, plus 2 dimension. Can also include k if it is 3 dimension, depends on the problem. Okay, so we have got I delta x plus j delta y. So this operator is given by this particular equation. Okay? So we have to remember this also, which we know. If you don't know or you don't remember, you're definitely going to use it in mathematical physics. Okay, that's going to be there. So let's consider a central. Okay, and then this central force is actually nothing but written as this. Okay, r cap into f of r bar, function of r. Obviously, function of r, since it's a central force. So if we actually just want to find out the magnitude, okay, we can actually represent it in this way. We can actually differentiate it with respect to the potential. So we already know that F is equal to minus of del U del R. In the previous section also we have seen that. So this is nothing but, if this is the magnitude, this entire thing is nothing but the magnitude and direction. Okay, and this minus del R can be written as only delta of U of R. Okay, so this delta would be nothing but this kind of representation that we have. Okay, so whenever you are writing down it in this way, okay, please understand this. Whenever you're writing down it in this form, you are talking only about the magnitude. You don't have a I, J, or K here, or you don't have any bar here. But as soon as you put a bar on this side, you are not writing down it as del R. You have to define which direction is del R, and that's why you have to use delta. So whenever you are writing down this function or this operator, this is a vector representation and not a scalar representation. Okay, so we have this, and then UR, which is nothing but the potential, is a scalar quantity. So I hope you remember that potential is a scalar quantity, right? Whenever you are doing your calculation, let's say you are using Gauss's law or you are calculating the potential. So when you are using Gauss's law to calculate the electric field is a vector quantity. It will actually have a direction. The resolution of vector is very important. But whenever you are calculating potential, the calculations are very easy, if you recall it. Okay, there we don't need to use any vectors. So in general, if you're dealing with scalars, sometimes the calculation becomes a bit easier. That we have to remember. Okay, anyway, so we have got UR as the scalar function. Okay, and you know that if we basically take the curl, okay, the curl of the gradient. So you know this is delta of UR, delta of UR, okay. And if you take another delta cross, delta is a vector, you're basically taking curl of the gradient of a scalar function, okay. So this will always be equal to 0. The curl of a gradient function is always 0, okay. So this you have to see. And if you can prove this, you know delta UR is nothing but F. So delta cross F is equal to 0. This actually shows mathematically that the energy is conserved. Okay, so how do I prove it? You can actually, what you can do is say this is basically a step which has taken help from mathematical concept. Okay, the concept of mathematics has been used to actually prove this. But what happens is, in general, if you are considering UR and you have got a form of UR in the form of vector, you take delta of UR, you get an answer. Then again, you take cross product with the delta. So when you take the cross product, you're basically going to get the answer as 0. Okay, and if you get that, you're always going to say that this is nothing but a conservative system. So if I say this, okay, if I write down in one sentence, whatever I said, central force, so Fr, whose magnitude is a function of the distance from the center of force, is a conservative one. Why conservative one? Again, I'll go back to this, because delta bar cross F bar is okay. So no doubt we can say that a force or energy or whatever will basically be a conservative one, whatever we have explained till now, if delta, let's say delta A by delta T is equal to 0. That means we know A is constant, so it is conservative. Here also, delta bar and F bar are in vectors, but the logic remains the same. It is delta X, delta Y, delta Z. We are getting 0, so that is nothing but conservative. So if you get a numerical problem on this, which you're definitely going to do in your mathematical physics class, and you take a cross product, you simply say this, right? You do it in this way: I, J, and K. These are all vectors, right? And then you can take whatever is the form of delta and whatever is the form of F. So delta would be nothing but delta X, okay? And then delta Y, and then delta Z. And F might have a form of, let's say, 2, 3, 4. Let's say it's 2I plus 3J plus 4K, something like that, the force form, okay? And if you take the cross product and you find this answer to be 0, okay, that means this is nothing but more or less a conservative system, okay? So don't show this example. I think this is okay. This is a basic logic. So you have to understand this and think about it, okay? Okay, so the next thing is conservation of angular momentum. So the question is, why angular momentum? Because, whenever we are considering a central force, the distance from the center is fixed. So whatever motion is going to be there is going to involve some kind of angle. Okay? It's not a linear motion. So not a linear momentum. It's a angular momentum. So whenever we talk about something in terms of angular momentum, we can directly involve torque, right? So torque we know. And what is torque? Torque is nothing but force into the displacement. Okay? In this case, it is nothing but the position vector that we're talking about. Okay? The cross product of force and displacement. Okay? So the torque exerted by the central force on the particle itself. Why torque? Question is, if I am going to talk about angular momentum, why I am talking about torque, right? Because force is related to momentum, dp by dt. Rate of change of momentum is nothing but force from Newton's second law. But here we are talking about angular momentum, so it's not going to be force; it is going to be the angular analog, that is torque, right? And this is not going to be linear momentum. This is going to be angular momentum. So this is dl by dt. It's very much logical that we are talking about torque. So the torque exerted by the central force on the particle is tau is equal to r cross. Okay. So please remember, except velocity. Velocity is equal to angular velocity cross the displacement, okay, or the distance. Okay. But whenever you take any other component, which is the rotational analog of the linear part, you will always have the rotational part is equal to linear part cross the distance. So except velocity, everything else has the same form. So if you have angular momentum, this is fine. Torque, this is fine. Okay. The angular momentum can be written in linear momentum term. Torque can be written in terms of the linear force and so on. Okay. So let's just do the replacements here. So this is R bar remains as it is, and F bar is nothing but you can write it down as R cap into the magnitude F r. So R cap cross, this is R bar by R, because R cap can be written as R bar by R. We already know it, but then this is R cap cross R. So cross product of, let's say, I cross I, J cross J, all are 0, right? So this is going to be 0. Going to be 0. Okay. So this is actually quite brilliantly proved by mathematical physics, okay, or mathematics rather. Okay. So this is very important. And then what we can say is this: we have tau bar is equal to del L del T, because we know torque is the rate of change of angular momentum, not linear momentum, is equal to 0. If this is 0, we can say that L is constant. L is constant, matlab angular momentum conserve हो चुका है, right? The angular momentum is conserved. So in general, we can say that the angular momentum about any axis to the center of force is constant. So angular force constant and angular momentum, right? So this is a different approach altogether to prove in case of a central force that the angular momentum and the total energy is constant. What is different here? The form of the force that we are considering. Please consider this. We've also seen before that the conservation of angular momentum is possible because we studied Lagrangian. There also we saw about conservation of angular momentum. But then where there we were talking about the linear motion, okay, the generalized velocity, the generalized momentum and so on. We did not consider really the angular part. Here we are talking about a central force, so we have to consider the angular part, take some help from mathematical physics and prove these features. In the next class, we are going to study about virial theory.